I invite the third presenters, Christophe and Justin, on Beyond the Pixels.
We live in a constant light field that directly affects our human biology. It has a high dynamic range of both natural and artificial light. We can try and capture this light field with a digital camera, but the relation to the physical light is lost in the complex and nonlinear ISP of the camera. We can go one step closer to and capture linear high dynamic range images as HDR brackets. However, the light is only represented up to scale. Conversely, to obtain photometric measurements, that is, the absolute light as perceived by the human eye, we need specialized tools such as the luminance meter that measures the amount of light in a given direction, and the chroma meter that measures the integral of the luminance over the whole hemisphere. However, those tools are expensive and limited to expert users. Because of those limitations, computer vision research was inherently limited in its ability to study the impact of light on humans. Can we bring photometry in the hands of everyone here and go beyond the linear pixel? In this work, we present the first large-scale photometric HDR dataset that we hope will enable the community to explore new problems in photometric computer vision. We have the chance to have access to a high-quality dataset of over 2,300 HDR panorama images of indoor scenes, the Laval Indoor HDR Dataset. We aim to calibrate the original camera to adapt the dataset to photometric values. This is the setup used for calibration. The camera captures an HDR bracket, and the chroma meters measures the true illuminance of the scene. The illuminance can then be computed from the HDR as a weighted integral of each pixel. In repeating this process for over 120 scenes, a linear relation arises between the measured and computed illuminance. Applying the slopes for each channel to the original dataset results in our novel photometric dataset.
Thanks to our photometrically calibrated dataset, for each scene, we now have the absolute luminance value in candela per square meters, or nits, for each pixel, as well as the absolute color temperature value in Kelvin. In order to showcase the diversity of the light field in our dataset, we have detected all the light sources in all the scenes. Here, when looking at a few examples, we can see that our dataset contains multiple types of light sources, ranging from bulbs to tubes to windows, and have a great variety of parameters, with sources with a color temperature ranging from 2 to 9,000 Kelvin, and an average luminance between 50 to 600,000 candela per square meters.
Our dataset allows us to explore novel photometric computer vision tasks. The new possibilities are many, but we focus on proposing baselines for 3 tasks. Let's share a few of our findings. In our tests, we compress the photometric image to an LDR, simulating the large ISP degradation. Firstly, we aim to predict per pixel luminance. We found that a baseline UNet produces results robust to ISP degradations. For the same UNet baseline, adapted to our second task, per pixel color prediction, it can learn the true color of the scene even when we augment the white balance of the input. This opens the door to white balance study under multiple illuminance. The third task is the prediction of hemisphere illuminance from a limited field of view. We observe that the RMSE worsens as the field of view is narrower. Finally, we experiment with generalization to another camera. To do so, we calibrated a point-and-shoot camera, 360 camera, and produced a smaller HDR photometric dataset. The experiments are run on the JPEGs directly produced by the camera's ISP. We find that fine-tuning is necessary to obtain good performance. Please see the paper for more details on the experiments. We hope to see you improve on those baselines and propose new photometric tasks. To help you with your research, both dataset and code are available right now. See you at poster 165 in room Nord. Thank you.
Thank you. I invite the